Okay, so I was asking Jeff, what's so classical about classical physics? What is it? What does it mean?
Like I know they thought like gravity was more like a ball on a string. Kind of this was.
Oh yeah, that's a good idea. That's a good example of classical physics. Yeah. There isn't any relativity there, general relativity. What else is an idea of classical physics? What kind of thing are we thinking of? Ball and a string is leading you into it, I think.
Projectile motion.
Projectiles, um, stuff that's really, really
Predictable.
Yeah, it's predictable because it's big. Right? Macroscopic is the word you're supposed to use, not microscopic. Everything we're talking about in this class is microscopic. Otherwise, there'd be no point to this class. So, but think about it. I mean, you started with the guys who could just think about things, and they weren't supposed to do experiments. And then you had the philosophers, and then you had the guys who started doing experiments, like Galileo got excommunicated because of it, but they let him back in. Did you know that? Our Catholic Church let him back in. Anyway, so you do experiments on macroscopic things and make macroscopic observations, and you could build a set of laws. It starts with an N, Kevin? Whose laws? There's 3 of them. Newton's laws, right? And yeah, predictions are fantastic. You can do really, really well. But the objects have to be big. Okay. So you apply these laws to something like this. I wonder, can I? Oh, doesn't work. Well, you might still be able to see it. Okay. You have a box, bunch of reflective material inside, and then you put a light inside. How does this thing work anyway? Why is there light being emitted?
Battery.
There's a battery, yeah. Why? You ever wonder about that? Huh?
Energy transfer?
Yeah, I guess, yeah, now that they haven't got away from, this conservation of energy. That's kind of a microscopic thing. That's true. Why is there light being generated?
The photon? The particle?
Yeah, you're jumping way ahead. Yeah, there's what this light actually is. It acts like a wave sometimes. Other times it acts like a particle, completely opposite spectrum. Spectrum's probably the wrong word, but completely opposite end of the ideas.
Light is both a wave and a particle.
Yeah, you're getting ahead. Why is there light?
Current runs through the filament in the bulb, and the bulb acts as a resistor. So like there's like an energy change or something. It has to emit light.
He's getting really close. The word resistor was huge. It gets really, really what? Hot. And you got to suck all the air out of here, otherwise it's going to that metal's going to react with the oxygen, and it's going to become brittle and just fall apart. So light bulbs, when you drop them, they implode, and they don't explode, right? They implode. But the point is it gets really, really hot. And this is the color it emits. So that's really what blackbody radiation is, except I'm doing this whole fancy box thing because I want to meet the definition of blackbody radiation. So you have a light source. We'll talk about what that light source is. And then it's emitted. After it's bounced around and reached this kind of light equilibrium inside. And then you measure the light intensity coming out, the wavelengths coming out. That's blackbody radiation. But it all started with something getting heated up. Okay? And in this case, it's a filament. And that's not how all light is generated. In fact, I think this is still an old bulb. Give it 5-10 years, we're not going to find this anymore. And this story isn't going to work because I'm going to have what type of light source? LEDs, light-emitting diodes. And we'll talk about that later. That's a whole other story. That's not blackbody radiation. So blackbody radiation take a look at it. What happened there? Here it is. Okay. This animation isn't the best because you're seeing all these colors. You're not supposed to see all these colors at 300 Kelvin. 300 Kelvin is about what temp? It's about what Celsius? It's about what Celsius? 300 Kelvin is around
23?
Is 18,
Or
was it 18 Celsius?
27?
yeah, 27. So subtract what from 300 and get it in Celsius? 273. So then you get around 27 degrees Celsius. What's the temperature of a room in Celsius? Yeah, around 20. So this is kind of like a hot room, 300 Kelvin. Okay, at 300 Kelvin, you take any object, and this plot is going to tell you the color that you should see. And it's going to start coming up, and you can see the colors. And we can zoom up as much as we want. We don't see any colors at 300 Kelvin. The whole point of blackbody radiation is it doesn't matter the object. It can be Gloriana's fingernail. It can be Jeff's pencil. It can be Alyssa's notebook. Any object. You heat it up to a certain temperature, they start glowing. So take any object. We'll take Kevin's earlobe. Okay, you lop it off, you heat it up to a certain temperature. 300 Kelvin, hot room. It's kind of gross. And you don't expect it to be glowing in the dark, right? You know it won't. So this line's flat. So whatever that object is, you heat it up. Now we're about an oven, 600 Kelvin. His earlobe still isn't glowing. Whoa, I zoomed up way too much. Let's zoom out. It's going up too fast. When will this thing start glowing red? We're getting some red now. See, so what's under the plot is the color that you're seeing. So it looks like you're going to start seeing some red first. Now we can probably zoom up a little bit and see it. So you're seeing some red now. And, all right, we're not even at the temperature of a light bulb yet, which is kind of good because if this is the temperature you heated that filament up to by applying the right current and voltage, right, that Jeff was talking about, man, that's going to be a real reddish looking bulb. So you want it to be even higher, that earlobe or that filament, whatever you're heating up. Okay, look at the light bulb. There it is. Now we got all the colors. Roy G. Biv. So the object doesn't matter. So if we zoom out, it's actually a little peak, right? So, and the funky thing about colors is that, you know, colors mix. So what color do you actually see, right? It's just going to look more like, and I don't know how much you've played with fire in camping, but fire is a lot of fun to play with, so I've played with it a lot. I know that you can get these, especially first when you go there the morning thereafter, right, after the big campfire, and you have those, they start digging in those coals, right? What's their color? Are they a bright orange or are they a really deep red after these coals have been around for a while? Yeah, you guys probably haven't done this.
Orange.
They're really deep red. So it's kind of like these coals aren't that hot anymore. So they're really deep red. See how the temperature is really low? It's a really deep red. If it was the middle of the campfire and you look in there, right, and it's these things that you've got the really nice TP thing going, you built your fire all nice, and you get those coals inside, man, they're a much brighter orange. The temperature's hotter, so that the peak shifted. So yeah, all these colors are there, but you know, some are more, your eye's more sensitive to some other than it is others. What color is your eye most sensitive to, by the way?
Red.
I would say no, simply because what are the colors that you see? Like the answer is red. I say no because what's the name of the guy? Roy G. Biv. Red is on the end. Your vision's falling off there.
So violet?
Violet is also on the end, right? So you can't see that very well either because it's Roy G. Biv.
So blue.
What's in the very middle? Yeah, kind of like that color that when LEDs first came out, they put those lime green LEDs on stuff. They lit up the whole room. I don't know if you recognize the color I'm talking about. I'm talking about that lime green LED. That's the peak of your sensitivity of your eye. And they pick red for taillights, not because it's, you know, you can barely see it. It's because it's really hard to scatter. Red goes for a long ways because it's a very long wavelength. We'll talk about that later. Anyway, so everything, if you heat it up enough, everything glows. Okay. So as you heat it up, what happens to that peak? It goes to a what and what wavelength? Longer or shorter? Right? I'm going to heat it up, heat it up, heat it up. Right? It's moving shorter. I should have asked you these questions first. What color is the longest wavelength? Red. The shortest? Violet. Yeah, this thing kind of tells you. Okay, so we played around with that enough. Oh, I think I just closed something I wasn't supposed to. Okay, Blackbody Radiation. Wein displacement law. Okay, so now they're trying to say, so you saw these curves, okay, and they're just trying to say that you can actually relate these things. C2 is just some constant, right, and they give it a name. What's CM? Is that a typo? CM just means, you've seen it, it just looks weird. CM is centimeter. Isn't that weird? Why would they pick centimeter? Anyway, that's just weird. So you can calculate the lambda max, right, the peak, just by plugging in the temperature, right, multiplying it by 1/5 C2. Okay, and they call it the Wein displacement law. We have our second radiate, no big deal. Total energy density. Total energy density. That means V is probably what, Gloriana? They're talking about density. Volume, yeah. This would probably have units of what? If we're talking about the metric system, Melissa. This energy density.
Is it milliliters?
Has to be standard metric units. So milliliters is a unit of volume, but not in the game we're going to be playing. What is standard metric units for volume?
Is it centimeters cubed?
Mm-mm.
Meters cubed.
Meters cubed. Energy, everybody's going to be what? Joules. So joules per cubic meter. And then we've Stefan-Boltzmann Law. It's not there. Why isn't it there? How do you draw that little thing? Something like that. I'm trying to draw that energy density symbol. Okay, it's trying to say the energy density is, Boltzmann got his name in here. A times T to the fourth. Now we don't even have a number for our A. That's okay. Okay, but they're just trying to say that as you crank up the temperature, you get more and more energy per unit volume. Right? It amplifies itself. It's T to the fourth. So these little things are coming up because they're trying to match this plot. Right? That they had a black body emitter and they just changed the temperature and they plotted out the wavelengths and how it goes like this. And what they keep, and they're not getting this to work out. But we're not get there yet. We're Neuronic Excitons, big M. Excitons, the definition of it is power over area. That's what really excitance is. Power over area. We've got the T to the fourth in there. And the sigma is our Stefan-Boltzmann constant. But so you can look at inside front cover to see what number that is. But what are the units of power? Watts. Area is, again, you got to stick with standard metric units. Squared meters. Yeah, watts per square meter. Okay. So I think Boltzmann is the guy who gets credit for this. That's how he got his name in here, but I don't think you need to worry about that. But I think what's interesting is that this classical physics, right, use Newton's laws and pretty much that's it. You get, here's the plot that you get. It's called the Rayleigh-Jeans formula. And it's not going to work. It's hard to see the applications of this. But if they would have made some more plots and given some more data, you would see that this guy, he's supposed to, if you're at the 30 Kelvin, you should see things glowing in the dark. If you heat it up a little bit more, you should get a sunburn from a hot pencil, just emitting all this UV radiation. You know, these things, it's way off. The equation's way off. So they call that the ultraviolet catastrophe, right? That you get all this UV ray from stuff. I mean, it doesn't even make sense energy-wise, right? You heat something up, it's going to emit UV rays. Okay, so we know that'll happen, but at extremely high temperatures, and you get this kind of plot going on. Anyway, so at some particular temperature, things will be glowing in the dark with the Rayleigh-Jeans. Now, it doesn't work. So what saved the day? Quantization of energy saved the day. Well, what does that mean, though? Quantization of energy. What does that mean to you, Melissa? Quantization of energy.
Amount of energy.
There's an amount of energy? Yeah, but the story goes on. Anybody help her out? What does it mean?
They measured the wavelength.
There's wavelengths. Jeffrey, do you have an idea? What's quantization of energy?
The numbers are just straight values, like 1, 2, 3.
Yeah, that's quantization. There's steps. There's only certain possibilities. I guess go back to this idea of, what's generating this light in this first place? Some object that you're heating up, right? You're just heating up some object. Well, remember with classical physics, I can take, I don't know, this remote control, and I can toss it to Kevin, and if we know the initial speed, the initial direction, and all this stuff, and we can actually calculate a trajectory like a projectile, right? We can spin it as fast as we want. We can, we've seen these types of things. If you want to get the right answers, no, you can't just toss this. Now, again, are we talking about a macroscopic size remote control? We're talking about microscopic. You have to go down to the microscopic to see quantization of energy. So we have to have a microscopic sized remote control. Now, how big is this going to be, Gloriana? What would you guess? What would be microscopic? To start seeing quantization of energy. And, well, we're going to talk about what that means, but how small would you have to get so that now funky things are going to happen? I can't just know the initial speed and the initial angle of this microscopic remote control. The size of an electron, definitely, for sure. You can even go a little bit bigger. But size of an electron and smaller, for sure. So if you get this remote control, the size of an electron, there we go. Now we're at the microscopic world. I'm going to toss it to Kevin. All we know is what? Hey, Kevin, I'll let it go. Yeah, I got it. I have no idea how it got here. Melissa hangs out under the table. And probably once in a century, and we're constantly tossing this back and forth for 100 years, she finally notices it below the table. That's the path it took. All she knows is that it was down there. So, and the point is that even those highly unlikely, seemingly energetically impossible paths are super important to get the right answers. So there's very odd things, but there's even more odd in the sense that it's only certain possible energies this little remote control can have. It's going to be even weirder in the sense where, well, I can twist this and swing it around whatever way I want. Not if it's microscopic. I can only twist it around at this angle. That's it. There's some very weird, anything that has to do with energy is quantized. So if this thing vibrates, I can get it to vibrate, right? Well, it can only take on certain vibrational energies. Anything to do with energy, it's quantized at the microscopic level. So once that's taken into account, man, boom, we can, well, it's down here. We can, the Debye formula, take into account quantization of energy. Now, I told you a lot more than what they knew at that point, but that's where we're getting. But if you take into account quantization of energy, man, the experiment and their calculations match perfectly. Okay. So then, I don't know if you remember, I don't know how important this is, but in PChem 1, we had the heat capacity of solids was 3 times R or something like that. So everything was hunky-dory, and everything's going great, except when they made these solids cold, this thing didn't match anymore. So then Einstein went in, and he's tried to fix this stuff up, but he assumed that everything was oscillating at the same frequency. Now, if everything's oscillating at the same frequency, this is more information than you need, but if everything's oscillating at the same frequency, how many energy levels are there? 1. And what we need to get used to, there's one equation. If I pick one frequency, I've got one energy. Here's another one. I pick one wavelength, I've got one energy. So when we say everything's at one frequency, we're saying everything's at one energy level. Everything only has one energy available. So he's kind of quantizing, yeah, but only one choice. So you needed multiple choices, but still being quantized. And then, so Debye figured that out. So he got his name on here, Debye formula, not the Einstein formula. I just thought that was kind of curious. I don't know why I even remember that. So let's keep going here. Quantization of energy example. The hydrogen atom. Whoa, let's allow it. Okay, so hydrogen atom should have how many protons? How many electrons? One of each, yeah. Okay, so there it is. What are these lines going out? Yeah, it's kind of sad, because if you're going to draw a hydrogen atom, is this what you're supposed to draw? Hopefully by the end of, when does this class end, like in May or whatever? I say, draw a hydrogen atom. I should put this on the final. Draw a hydrogen atom. If you draw this, I'm going to take my remote control and whack you on the back of the head. Okay? Because how you should draw a hydrogen atom isn't this. That's why I wish they didn't do it. But
Didn't you draw it like a door was going in
yeah, something like that. So you can make a dot or something, say that your nucleus is, but then anything goes. I mean, make a big blob. You can make the blob have different shapes, whatever, and just say 99.9% of the time the electron's in there, even inside the nucleus, whatever kind of blob you want. And then the more shape it has, what that really means is that you're at a higher energy level. Because it's kind of like when you take a string or a wave. Take a wave, right? And if you, I don't know, you guys probably don't. It'd have to be really hard to play in a swimming pool to do this. But you go in to the swimming pool when it's really flat, right? Really flat. Just try to see if you can imagine this. And you slowly move your hands in and out, okay, to try to build waves, but be in sync, okay? And then I don't know if you can imagine it. Can you imagine the little crests and troughs that you're, right? And they start building on each other, okay, because you're in sync. The water bounces back, and right, everything's in sync. Okay, then you do the exact same thing again, but a little bit faster. Right? You don't see waves. What you end up seeing is a peak, and they don't move. Peak, trough, peak, trough, peak, trough. And we'll have some animations of that later. But the point is, you get a lot more spots where there isn't any movement, and that's a higher energy. That's kind of what's going on here with a wave. If you made more shapes, how I'd make a big blob and a small blob. But see how there's different shapes? Anyway, that's how you draw a hydrogen atom. But we'll worry about that later. Where am I? Oh, it was because of that stupid picture they had. Okay, so this is just to play around with it and say that, okay, I'm going to shine, you can shoot whatever photons you want at this thing and change the wavelength. Where do I change the wavelength? Here it is. And it doesn't absorb. It has to perfectly match a line. And I can't even get I can't get the scroll bar to match a line. You know a line? These guys. Do you remember, man, I think it was general chemistry, didn't we? Didn't we show a lamp, then you had to look through it through a black spectroscope, and then you saw all these different colors? I should have brought that in here.
I think Gen Chem, wasn't it?
Is that Gen Chem?
Mm-hmm.
I should have brought that in here, because you're actually seeing all the energy levels. And that's really what this is. Just take this on its side, and then you'd see all those different colors. So I can't take the scroll bar to match a line, so I have to actually click on a line. And then it shines it, and then it jumps up to the first line. See how it jumped up to the very first one? It has to exactly match, and then it jumped back down. Okay, so this is just playing around with that. It's not really much to show you, right? But the light you shine has to actually match an energy level. Then it jumped down to this one, and that will jump down to the last one. And what is it emitting? A photon. That actually matches this energy level difference. Remember, E equals h nu, or hc over lambda. Okay. Wave-particle duality. I think the movie was called Scanners. I got to Google this and look this up. But it was a black and white movie, and this guy shined the de Broglie wavelength of people's heads. And what he did is he called them, and then that frequency went through the phone, and their heads started oscillating, and it just blew up. If you're driving a semi-trailer down a road, and if there are some bumps in that road that make the tires vibrate a little bit, not huge bumps, just something that makes everything vibrate. And if that vibration perfectly matches the de Broglie wavelength of a big honking thing strapped down, it starts oscillating. It starts grabbing that energy and oscillating, and then it can just bounce out of there and can move. It happened to a bridge. Let's see if I can get this to work. So before I show you the video, again, these engineers, they're supposed to have watched this, and the de Broglie wavelength of this bridge, there's some winds or whatever got this thing to vibrate. It had to be the winds. I don't really quite understand how the winds did it, but the energy of the winds got this thing to start oscillating at its de Broglie wavelength. Everybody's got a de Broglie wavelength. If you shined my de Broglie wavelength on me and my body would start absorbing it, my wave nature would just start resonating, and you'd see I'd start vibrating up and down and jumping around. So everybody's got a de Broglie wavelength. The de Broglie wavelength of these macroscopic objects, though, is really, really small or big. The equation is a huge hint. If you know what P is, and if you know what H is. What's H? Planck's constant. That's 10 to the negative 34. So 33 zeros and a 1. That's in the numerator. Then you're dividing it by P. You're making it even smaller. What's P?
Is that low or P?
Little p. momentum. Momentum is what times what?
Mass times volume.
Mass times, you're close, mv, not mass times volume, mass times speed. So, and put those in standard metric units. So you're going to have your kilograms or these, I mean, it's ridiculously small. You can't measure these things. But it happens. So the Tacoma Bridge, and I don't know where it was, Delaware or something, but it fell apart because everything has de Broglie wavelength.
Is that in real time?
Yeah. Well, look how old it is. It has to be real time.
That
Right.
really happened?
Yeah.
How?
Like I said, I think there's a car on there even. It's the, you can Google it and find out more about the Tacoma Bridge. I don't think it withheld. Maybe the wind stopped and it died down and it stopped doing it.
How does concrete do that?
So it's, no, it's not concrete. That's a suspension bridge. It's iron, right? It's something that can give. But the problem is that it just started oscillating, got worse and worse and worse. It just absorbed the energy. Okay, I probably did after a while. And then we're supposed to talk about photoelectric effect. So all these things you can't explain with classical physics. So you can't explain, right? Classical physics says that objects want to glow in the dark. Classical physics can't explain why hydrogen will only emit certain colors, right? It's like saying I'm going to toss Gloriana a volleyball, and I can only toss it at 1 mile per hour and 10 miles an hour. That's it, and nothing in between. And I can only throw it with my right hand on Wednesdays or something. So it's weird. There's no explanation for it. So, and this is the last, and then this de Broglie relation, another failure of classical physics. And then there's one more that they slammed in here, photoelectric effect. So you can't explain this either. So here it is. We have sodium metal. That's our target. So what's our target? See how here's your light source? So this must be your target. And this is sodium metal. So we can shine whatever light we want on there. Whoop, I have no intensity. Crank up the intensity, right? Whoa, it's already giving you a hint what's going on here. I don't want to do that yet. Okay, so the point is I can shine whatever intensity I want and whatever wavelength I want. Okay, so I'm going to turn on the battery. So now if any electrons are kicked out of here, right? If the light kicks out some electrons, they'll fly out of here and go to here. Okay, so I have 0 intensity now. What's high energy? Over here or over here? The red, right? So let's start out there, and let's start out with really intense. Okay, so it's not kicking out any electrons. If see, intensity doesn't matter. If I go a little bit lower, see, intensity doesn't seem to do much. Keep going lower, lower, lower. I'm in that lime green color. Ooh, I got something. What happens if I roll the intensity? If I make it more intense, I should get more particles, I would think. All right. Make it less intense. Well, that's 0. I can't make it 0. But even though it's less intense, you still get something out of there. So the idea here is that intensity doesn't matter. When you're trying to answer the question, will an electron be ejected? All that matters is the wavelength of the light. If I go even more energetic, right, I get more electrons. But see how the determining factor isn't how intense the light is. The determining factor is the wavelength. It'll totally stop, or I'll get something ejected. So that energy that's needed to kick out one wavelength. Remember, energy matches wavelength. So Once you reach that threshold, it'll kick out an electron. And that's called the photoelectric effect. The energy threshold that you have to overcome is called the work function. They have it that symbol. So if you're going to, I think this is even one of the homework questions. If you're going to, what's the speed of an ejected electron? I'm sure though there's much more words to this. And they're going to say they're shining some light on some metal, right? And they give you all this data and all this information. And the question at the end is, what's the speed of the ejected electron? Okay. So even though it's microscopic, we still have the energy conservation idea. So you have the incoming energy. That has to equal, I guess you could say incoming. Get this idea down. Incoming energy. That has to equal, okay, well, you got this electron being ejected, so that's going to have some kinetic energy, right? But then it had to get pulled out of the metal in the first place, and that's that work function idea. All right? So this is just going to be so many joules, and they need to tell you what that is. What's the equation for kinetic energy? 1/2 mv squared. So my answer is going to be what symbol? I'm after the speed of the ejected electron. My answer is going to be little. What's m? Mass of the electron. So we're talking about kinetic energy of the electron, so it's the mass of the electron flying around. Better have it in kilograms and look it up somewhere. What's v? Which is speed, and that's what we're looking for. So we're going to have to solve for that v to answer this question. What's the incoming energy in this photoelectric effect?
The wavelength of the light.
Yeah, the wavelength of the light. Now, what's the equation for the energy of a photon with wavelength in there?
Say that again?
What's the equation for this photon of light in terms of wavelength? You have to have wavelength in there.
H. Max constant times lambda.
H, I think it's hc over lambda. I think it's hc over lambda.
Yeah.
So you can write h nu here, but that really doesn't help you because, right, they're going to give you a wavelength. And you just solve for v. So I think that's your hardest homework question. See, so it's going to be easy. Easy schmeezy. Make sense? Wave-particle duality. I think Kevin or someone already talked about that. Light. What are some names of light? We say light. Light is supposed to be covering everything. What does light cover, that word light? What else could you use for the word light? Give me an example. Infrared. That's light. What else could you say?
Ultraviolet.
Ultraviolet.
Micro.
Microwaves.
I'm not-
Radio waves. X-rays. Gamma rays. All that stuff is light. Light is composed of energy, photons. Okay? And this energy, or this photon, can be distributed for infinity. Then it's acting like a wave. It's acting like a wave when you see these diffraction patterns. But it's acting like a what in the photoelectric effect? It's acting like a particle for sure, man. This energy is all combined into one hard thing that's concentrated somehow, and bam, it knocks out an electron. If it's energetic enough to overcome the threshold of the metal that's holding the electron in the first place. So the wave-particle duality. I think the de Broglie effect, objects actually have a wave-particle duality. When you think about it, with the de Broglie wavelength. So does it look like I would have to be moving, wouldn't I, to have a de Broglie wavelength? Because P is m times V. So I can't just be standing here. I have to be like that crate in the back of a truck. I'd have to be moving. So once I'm moving, then you can actually calculate my de Broglie wavelength. So in that sense, that movie was kind of off. Those dudes had to have been walking or jogging or been in a car or something when their head's going to get blown up in that movie Scanners, right?
Up the bridge.
Now the bridge, I think it had to get moving, and the wind had to got it. I think we like to think of P as m times V. We like to think of it as, okay, I don't want to throw that. This is the only type of speed, right? But if you just, wind's blowing, it's moving. It has speed, right? So I think it needs to be moving. So there's different types of motion other than just translation. Okay, there's vibrational. There's rotational. There's mixtures of the two. Okay.
Yeah, we don't have
The homework typed out on our book.
Yo, you don't have it typed out?
We did this.
How about in any of the chapters? Do you have them typed out?
Nope.
No, go to the next chapter.
I am on the next chapter. Here it is. It's right there.
Oh, man.
You sent the wrong thing? Where
I
did you get
sent-
to do this?
I sent the wrong file.
How dare you?
$30.
You messed up, Dr. Smith.
Right, at least 15 of that.
Why does mine have it? Yours, that doesn't make any sense.
You send them that file?
These are the only files I have.
Maybe they're somewhere else.
So in no chapter they're typed up. Doesn't make sense. No, they can't change the order of my files. I couldn't have sent it to them. I had to have sent them one that didn't have this. Wow. You actually got to bring your book.
Ew.
You know what I could do? I could print out these pages and then you just kind of tape them in there.
I would
Right?
Bring the book. Let's just bring the book, you guys.
More paperwork for you.
Yeah.
No, you tape them in. Right?
Not about that life.
Yeah, because look at all the space you'd have. Don't you? Or not?
I'd rather not. I'd just rather bring my book and have it on
I
a
can always
separate
look
sheet.
it up in there.
Yeah, I'd rather not bring my book. I'd rather do neither.
All right. Bring your book. You're going to have to bring your book to class.
Alright.
Determine the wavelength of the radiation of the most intense. That's why I brought this so I can read them. That sucks. This does no good.
We're done.
Well, we've got 3 minutes. Determine the wavelength of the radiation of the most intense electromagnetic radiation emitted from the surface of the star Sirius, which has a surface temperature of 11,000 Kelvin. It looks like probably what relationship are they shooting for here? Yeah, I think so too. The one with lambda max in it, right? That'd be straightforward.
Which one?
The one with that Wien displacement law, the one with lambda max in it.
Lambda. Oh, I see it.
Because they want the most intense, the wavelength of the most intense, so that's lambda max. In the next one, calculate the power radiated by 2 by 3 meter section of the surface of a hot body at 1500 Kelvin. They're probably referring to what? Yeah, because that M is what over what? What were the units? Watts over square meters. So you solve for the watts. Here's the square meters. Okay. Energy per photon. See, so you see, I don't think these are too bad, right? So if you have some questions, just come by. I'll be glad to help you out with this stuff.